This video is going to cover how to calculate the critical column load, which normally we call the buckling load of the column. We have a fancy equation for it, and that's PCR, which stands for P critical, so the critical column load, and that's equal to pi squared times EI over the length effective squared. EI we already have talked about before, and that's flexural rigidity. E is the modulus of elasticity, I is the moment of inertia. Which one you do, that's dependent on what you're trying to find. And again, L effective here, L sub E, is the effective length, which is effectively unbraced length, but it's a little bit more than that. So let's talk about that one first. We have multiple different types of columns that we can have, and it's based on their supports. So if you have a pin or pin roller or whatever, it's supported there up at the top. If you have a pin, we're going to have a K value of 1.0. This has to do with the shape of the curve. And that shape is a half sine curve, and we're going to call that normal. Then if you have a fixed pin, so fixed at the one side, and again, pin or roller, doesn't matter, on the top, a fixed pin is going to have a very interesting shape. It's going to start off to be kind of flat, and then it's going to kind of curve out from there. And that ugly way of doing things, that K value is then going to be 0.7. If you have a fix column, not very straight there, but whatever, if you have a fixed column, it's going to be kind of straight at both ends, and then it's going to kind of curve. And that one's only going to be about half the size, so this K value is 0.5. And lastly, if we have a fixed free, where it just, is free to do whatever it really wants, then you have, it's kind of straight, but then it's going to be, off at whatever angle it wants. So this dude can really do whatever it wants, and that's, you can see, kind of half of a sine curve, so this K is going to be 2.0. So those are our different K values, and L effective is just K times the length. Yeah, that's all he actually really is. So when doing this, effectively you have a column, which shape-wise doesn't really matter what it is, but you have a column here, and you have your load acting right on it, and you want to know what the maximum is for buckling. But again, buckling is based on EI, I the moment of inertia. So which one are you supposed to take? It can technically buckle in two different directions. It could be buckling this way, where it pops out that way, or it could be buckling this way. Which one is it going to do? Technically, if the supports were the exact same, then the smaller I will control. But that's only if the supports are the same on each side. If they're not the same, then obviously you got to check both. So the real question becomes, how do I know which I I'm supposed to be using for my P critical? And really think of it like bending, because effectively that's what's going on, right? It is bending. Just imagine you have a moment and it's bending, right? So if it's gonna pop out here in, this, we'll call this, the X direction. If it's popping out in the X direction, technically we're going to be bending about the Y. So kind of like how bending was when you think of your bending equation. We had M, if we said mx, it was times y over ix. So you see how those things were opposite each other? It's the same thing that's going on here. If we want to find P critical in the X direction, we're talking about how much movement it could possibly pop out in the X direction, then we're going to be doing two things. We're going to look at the X direction constraints. Probably shouldn't write that there. So we're looking at X constraints, or the X restraints, I guess that's how I wrote it. So what's going on up here? How is it being restrained? Is it pin? Is it fixed? What does the bottom look like? Is it pin also? Is it fixed? Is it fixed? Is it fixed free? Like, what are the restraints? What are the supports looking like? And when we're looking for those restraints in the X direction, then we're going to be using the moment, or the moment of inertia here, in the Y direction. So when we say look at restraints, we're talking L effective for the X, and then we're talking IY. And same thing if we were to try and find P critical in the Y direction, then we're going to be looking at the restraints in the Y. So we'll have L effective Y, and we're going to be then using IX. Kind of like an equal and opposite. But again, that comes from our bending equation, because that's how bending works, right? It's going to bend about the other axis when it's going to be moving in the perpendicular direction. So like, for instance, you have an I shape here. I'm just going to make it a built-up one just because I'm not really good right now with drawings. So here I have my little I shape. We have the x-axis and we have the y-axis. If it bends about x, this thing is either going to, from the side, if it's bending about x, here we have our side shot of this thing. If we're bending about x-axis, this is going to cause this member to kind of, if we had like an axis here, it's going to pop upward or downward. So this is y direction movement when we're bending about the x-axis. That's where it all comes from. So the trickiest part about using this equation is making sure you're getting the right directions, because if you put the wrong directions in, you're going to get a very wrong answer. So let's do an example. So for this example, we're going to have different restraints. We're going to have an I shape, so please look at the picture right there. And we're going to have a column. And for our column, we're going to say that in this direction, P is right here at the dead center at the top. He's going to be fixed, and he's going to be restrained in motion in the Y direction. Okay, because we're looking at this dude right here. We're currently looking at it this direction, so he can't go, there's a roller, and there's a roller. So he can't move in the Y. Okay, so that's what we're really paying attention to. Can't really move in the Y. We're going to call this our front face. And then from the side, you turn it around and you look the other direction. This time you really don't see anything, you just see the top flange. So here's the web, skinny little piece. There, here's the web, and again, P at the dead center. And we're going to say that he's just not restrained. So again, there's a roller right here on each side, but as far as movement goes this way, he's kind of unrestrained. So he can move along in the X direction, but he can't really move along in our Y direction. Okay, and I'm going to call this the side face, just for ease of talking. No matter what, though, this column is going to be 35 feet tall. He's a pretty tall column. Pretty tall. And the type of member we're going to have, we'll say he's a W12 by 14. Okay, so W12 by 14. We can go to Appendix B, and in Appendix B, where it has all of those, properties laid out, we'll get IX for this as 88.6 inches to the fourth, and we'll read that IY is a whopping 2.36 inches to the fourth. So again, usually the way that we load these things is because obviously Ix is stronger. And again, the smaller I is making it weaker, correct? So that's kind of like a hint of what's going to go on. So the way that we always load things is because of the vast difference in moment of inertias across the x-axis and the y-axis. That's why you don't see H's very often in terms of beams. So what we want to do for this example is we want to find P critical. Yeah, that's really not much. This is really, they'd call it the maximum load. Right? What's the maximum load you could put on this column? That's all we really want to find. So it's made of steel, right? And we know that steel has a modulus of elasticity of 29,000 KSI. So that's wonderful. So now let's talk about our different directions. They didn't really draw it, but again, we can kind of draw it. And let's say that this was direction, movement direction. This is the y. As far as movement direction goes this way, this is x. So let's talk first. Let's talk movement in x. So movement in the x, what do we have here? Are we restrained? Well, it's fixed, free. So fixed free here, we're going to have k is equal to 2.0. And then we're going to calculate L, effective. So k of 2.0 times the length of 35 feet. Okay, cool. So obviously you get 70 feet. Who would have guessed? Now you're going to have to trust me on this one just for a moment here, but we really don't want it in feet. It really would be better if it's in inches. I know it sounds kind of silly, but really it is. And this one's going to be 840 inches. Now let's talk movement in the y direction. So movement in the y direction, very obviously it's restrained, right? It's going to be fixed pin. I know it's a roller, but again, it doesn't actually matter for that purpose. So k for this guy is going to be 0.7. Cool. So now what? Calculating LE again for this one, we have a 0.7 for the k, and we have a length of still 35 feet. So obviously he's not as big, right? So obviously we're going to get 24.5 feet. And again, we don't like feet. We're going to turn that into inches. So 24.5 feet turned into inches is 294 inches. So we have our two different L's and our equation. Remember P critical here. If we're going to do the x direction, it's pi squared times E, which E is, I'm just going to write it, E times I. Again, this is going to be I in the y-axis if it's moving in the x direction, divided by LE for the x direction squared. So remember that E is going to be 29,000 KSI, okay? And then IY we have in inches as well, which is 2.36 inches to the fourth. You can now kind of guess why we have our inches for our length here. And then we're going to plug in, we said the x direction movements. We're looking at the restraints in the x direction, so that's 840. Again, it was in inches because now we're going to square that. Now we have inches squared and inches to the fourth on the top, and then kips per square inch. So we're going to get a value for P critical in the x direction here of 0.957 kips. So actually 957 pounds. You might be thinking that's rather small. Well, yeah, because again, our smaller moment of inertia here is really not doing us any good. And if we want to find P critical in the y direction, again, that's going to be pi squared times E. who again is 29,000 KSI. This time though, we're looking for bending in the y, so we're going to multiply by Ix, who is 88.6 inches to the fourth, and divided by our effective length in the y direction, which was 294 inches. And then don't forget, we're going to square that number. So what we're going to get for this dude is 293 kips. Wow, what's the maximum we can put on this column? Well, sure as hell is not 293. Nope, it's going to be 957 pounds. Because once you go past that, obviously it's going to buckle in the x direction. So, like I said before, obviously the moment of inertia, you're thinking, oh, the smaller one's definitely going to control. That's literally just based on the supports that we have going on with our problem and the member that we picked. Technically, if you want to see how much these supports matter, let's switch the supports. So this time, instead, we're going to say that the rollers weren't here. The rollers were over here instead. Okay, how much is this going to affect it? Really, all that's happening is that this is now going to be the y direction, and this is now going to be the x direction. So I'm going to swap these two numbers. How much of a difference is that going to make? If I swap those two numbers, then P critical in the x direction is pi squared times, again, 29,000 KSI times 2.36 inches to the fourth. It's still the weak axis. Divided by, we said we're going to swap it. It's going to be 294 squared. Inches squared, technically. And what do we get for the x direction? Now we get 7.81 kips. Okay, that's quite the improvement, but what then happens for the y direction? Well, this one's now pi squared times 29,000 KSI, and then also times 88.6 inches to the fourth, divided by this one is now 840 inches squared. So we're going to get this time 35.9 kips. And you're still thinking, yeah, well, this guy's still controlled. I mean, do I only need to check one? Again, depending on the shape, this one has a very radical difference between Ix and Iy. If it's not quite so radical and our supports are definitely different, then obviously it's not always going to control. And again, it's not hard to just check both, so do always check both because you never want to be the person who only checks one and causes a failure. But that's really all that there is to it, to finding the critical buckling load of a column.